Okay. 6.3 talks about the derivative of the other four trigonometric functions. So, derivative of secant is secant tangent, derivative of tangent is secant squared. This is pretty much how I really remember it. When you take a derivative of sine of x, that's the cosine of x. And when you take a derivative of the cosine of x, that's negative the sine of x. So, the way I had it memorized, I memorized that the derivative of sine is cosine, derivative of secant is secant tangent, and derivative of tangent is secant squared. And when I take a derivative of cosine, I get the sine. When I take a derivative of cosine, I'll get the sine with a negative. When I take a derivative, if I have that memorized, derivative of cosecant, since derivative of secant is secant tangent, derivative of cosecant is cosecant cotangent with a negative. And if I took a derivative of tangents, that's the secant squared. So derivative of cotangent would be the cosecant squared with a negative again. So the way I memorized the yellow 3 part. 1, 2, 3. And from there, I just mimicked when I take a derivative of the cosine, cosecant, cotangent, I associate them with the sine, secant, and tangent, except they have a negative. Let me show you one of those. It doesn't matter which one. If I pick the derivative, let's show the derivative of tangent is secant squared, for example. Well, this is what we know. If y equals tan of x, that is sine of x over cosine of x. And if I was going to show the derivative of secant, I would have wrote y equals secant of x, which is 1 over cosine of x. And when I take a derivative, I would use the quotient rule. Derivative of the top times the denominator minus the top times derivative of the denominator all over the denominator squared. And that would be the cosine squared of x plus the sine squared of x all over cosine squared of x. And if you remember from 6.1, sine squared plus cosine squared is 1, and 1 over cosine is the secant squared of x. And there it is. Very simple to show. You could pick any of those. If I want to show the derivative, I'm sorry, I kind of messed up. Okay. If I want to take a derivative of cosecant, if y equal the cosecant of x, for example, I'll say that's 1 over the sine of x. And when I take a derivative, that's going to be derivative of the top times the bottom minus the top times derivative of sine, which is the cosine of x, all over the denominator squared. dy dx would be, that's a 0, that's negative the cosine of x over sine of x times sine of x. And if I look at those, cosine over sine is the cotan of x, and 1 over the sine is the cosecant of x. And there it is. And that's how you derive any of them. Well, the important part here, you're not going to be asked to derive those unless the homework asks you to do it, but that's how you'll do it. You're going to just have to remember those derivatives. And let's get this out of the way really quick. So, derivative of anything with a c. Cotangent, cosecant, and cosine will give you a negative. That's how I remembered it back in the day. So, dy dx twice. Derivative of tangent is secant squared. I memorized that, times 7x, right? Of 7x, I'm sorry. Times the derivative of the angle, which is a 7. Again, that's a fine answer on a test, especially if it says do not simplify. For the homework, I would like you to simplify as much as possible. And here we are, derivative of cotangent. Well, y prime is going to be derivative of tangent is secant squared, so cotangent cosecant squared with a negative of the angle times the derivative of the angle. Again, there's nothing wrong with that answer, but the authors always like to write the trig function last, especially if there's a variable matching the angle. If I want to take a derivative of secant, I know that the derivative of secant is secant tangent. So derivative of secant is secant of whatever that angle is, tangent of whatever that angle is, times the derivative of the angle. Well, again, a square root appears a lot more than we like. It's worth memorizing just for square root that a derivative of square root is 1 over twice the square root of x. This is a fine answer on a test. For the homework, you need to clean that up. Y prime equals negative secant of radical x tangent of radical x all over radical x. This is actually cosecant of 2x to the 1/3 power. Let me lift that problem a bit up. If I take a derivative, bring the power down, subtract 1 from the power of whatever the radicand is, times the derivative. Well, we said derivative of secant is secant tangent. Derivative of cosecant is cosecant cotangent with one minor change. It picks a minus. Times the derivative of the angle, which is a 2. By the way, the angle is called the argument, but we're not going to be that picky. That comes up in your future courses. Again, on a test, this is fine. For the homework, it's going to be negative twice the cosecant of 2x, the cotangent of 2x, divided by 3 the cube root of cosecant of 2x squared, or you could make the cosecant squared in there. It doesn't really matter. So something that you're going to have to make, and that comes up a lot. If I'm looking at x to the 2/3, either you say that is the cube root of x squared, or you say that's the cube root of x squared. It turns out this is more beneficial, but for what we need, either one will do. I feel like I'm squishing those. You know what? I'm going to start spreading out the examples more. I feel like those are really squished together. Maybe do 3 per row. I have plenty of space. How about here? Well, now it becomes redundant. Y prime is the product rule. Derivative of the first, which is 1 times the second, plus t times derivative of cosine is cotan. I'm sorry. Why did I see it as cosine? Cotan. So 1 times the cotan of 3t plus t times derivative of tangent is secant squared. Derivative of cotangent is cosecant squared with a negative, times, of course, by the chain rule, derivative of the angle, and that's going to be cotan of 3t minus 3t, the cosecant squared of 3t. Again, the product rule, y prime will be derivative of the first times the second, plus the first derivative of tangent is secant squared. That's a fine answer. You want to clean it up a bit, you can. That would be tangent of x over twice radical x. Again, this doesn't mean this is more simplified, but whatever works. Again, I have no problem with you leaving the answer like that. And part G, the same deal. If I take y prime, derivative of secant is secant tangent, derivative of cosecant is cosecant cotangent with a negative, times x cubed plus 1 minus derivative of the denominator, which is 3x squared times the top, all over the denominator squared. And that's a fine answer. You could leave your answer like that. You could, if you wish, and that's not, again, that's not more simplified, you could factor a cosecant, negative cosecant of x out to have x cubed plus 1 cotan of x plus 3x squared, if you really want. But this is not more simplified. All over x cubed plus 1 squared. This is a fine answer, and this is a fine answer. And we're going to touch on implicit slightly. Now this is when you don't have y equal. Find the implicit differentiate using implicit, however you want to read it. Well, derivative of a power function, bring the power down, subtract 1 from the power, times the derivative of y, which is dy dx. Derivative of cosecant is negative cosecant of x cotan of x. Remember, you need to solve for dy dx. So dy dx would be negative cosecant of x cotan of x divided by 2y. Implicit appears a lot more than you like as well. Something you should get out of the way. And implicit is when you don't have y equal, y is present in both sides of the equation. Here, if I want to take a derivative, I would say dy dx would be derivative of sine is the cosine of the angle or the argument, times derivative of this. Derivative of x is 1. Derivative of negative 2y is negative 2 dy dx. So here, you always have to solve because you want dy dx on one side, everything else on the other side, just like we did in the previous problems. Well, if I distribute that in, I'll get dy dx to be cosine of x minus 2y minus 2 cosine of x minus 2y dy dx. If I get all the dy dx's on one side, if I factor a dy dx, if I factor a dy dx out of both of those, if I factor dy dx, I'll get a 1 and a dy dx plus twice the cosine of x minus 2. And that would be my answer. So implicit always takes a bit more work because you have a few more steps to fill in. It's never as simple as traditional, straightforward differentiation. And if I look at part K, the same deal, derivative of sine, that's the cosine of y, dy dx. You could start using y prime if you're really comfortable with that. Here we have the product rule, derivative of the first times the second, plus the first times derivative of y is y prime, and derivative of 3x is a 3. Remember, I need to get y primes on one side. So y prime cosine of y minus y prime x cubed equals 3x squared y plus 3. If I factor a y prime, I'll have a cosine of y minus x cubed. That's the step I skipped on the previous problem, and y prime would be 3x squared y plus 3. Since this is being multiplied, you divide both sides by it, and there it is. And that's pretty much a quick catch on the derivative of the other trigonometric functions. So 6 trigonometric functions altogether.